Shall I start that way? Let's wait
Yeah.
2 minutes. Let's wait 2 minutes.
It's up to you. You decide, okay?
Let's wait till 12 and we'll start. Okay. All right, so welcome everyone to this module, I guess it is called, of the class on ominimal structures. I'm sorry that I can't say hello to everyone. I'm not sure I see even the participants on the side, and I'm not seeing everyone. So hello to everyone. The plan is that I do this class and Friday's class online, and hopefully I will by Sunday be in Toronto, and I will continue the classes actually on board, which will be nice, which is something I haven't done in 2 years. It would be nice to do that. I will be talking mostly on joint work with Sergei Starchenko, which is quite old by now, probably 15 almost years or more, 20 even years sometimes. And the title is Complex Analysis in All Minimal Expansions. The word expansions is missing. Expansions of real closed fields. And I put a list of references to which actually goes back to an article of Fortuna and Loyashevich from the 80s, where they touched on subjects like that in the semi-algebraic setting, and then contains all the references to our work. And I just included the reference for the recent applications of all these subjects. So this is the work on O-minimal Gaga, which I guess will be part of the subject of Jacob Zimmerman's module right after mine. Another thing that I did, and I will try to do from time to time if there is interest, if not, I'm not sure I will continue with that. I put one problem set on the workshop page, and I think it's nice. I will say in few slides on, I will say what this current problem set covers. And I think it's a nice exercise for people who know basic O-minimality. I will mention in a second what is there. Now, the goal of the whole project here, the goal of this module is to develop basics of, I'll call it complex analysis. It will not be over the complex numbers. Complex analysis, sorry, I'll make this straight. In arbitrary, and I'll talk about it in a second, arbitrary O-minimal expansions of RCF, which will stand for real closed fields. Now, this really captures maybe 2 or 3 levels of generalities that I want to talk about. So I will talk about details will come soon, but this will be all minimal, and whatever it means to do complex analysis here, this is what we will do. And let me point out that there are various levels of generalizations that we are doing here. So one thing that, okay, I'm going to try to do it like this, and then you will have always the last page online. So this contains or captures several things. First thing, we will identify in this way, in particular, the unique properties of complex analytic, real complex analytic sets, functions, which are definable in structures over the reals, which are all minimal. Okay, notice the difference that here it's actually the reals. So in some sense, this is what applications are interested in. We want to know what happens really in the complex number, the actual complex numbers. Because we are doing model theory, what we do actually, and we could have done, so this could have been a class by its own. I could have done a class on just definable functions and sets in all minimal expansions of the real numbers. By the way, if you have questions that we can try, I can try to answer if you just shout them in. If something is not clear, I mean, I don't mind. You don't have to raise hand, just unmute yourself and ask. And if we see that it doesn't work time-wise, I will tell you, but please feel free to ask questions just by unmuting yourself and shouting the question. Okay, so this is one thing we could have done. This could have been a class. Take the reals with the analysis that we know and try to understand what is true or not true for particular, not arbitrary objects, but objects definable in all minimal structures. Now, another level of generality we could have done is to say, okay, we are doing model theory. So let's talk about, not about actually the complex numbers and the real numbers, but instead, let's allow ourselves a little bit more definable in structures which are elementarily equivalent to structures coming from the real numbers. As we know, and we will talk about that, when you prove results about structures like that, you basically prove results about definable families of objects in the original structure over the real. So this level of generality is useful. It's not just for mere generality, because, as I said, when you prove on results on structures like that, you know also more information. It's usually about parameterizations of objects in the original structure. But actually what we will do after consultation with Patrick, we will do a more general approach, and we will actually do something more general. We will develop the theory without assuming that our structure is elementarily equivalent to structure over the reals in arbitrary all minimal extensions of real closed fields. And I hope, I think tomorrow even, to talk about a whole family of examples that live in 3 and actually does not live in 2. So There are structures that were developed by, I think, first by Lipschitz and Robinson, and then Kluckers, I think, joined them and wrote another paper with them. There is a whole family of homonomial structures that haven't been studied very extensively. And maybe the only place that they were studied was to refute a theorem of conjecture of Van den Dries. But I think they could be useful, and we'll get to that. And for example, what we will do will fit into that setting, which is provably not elementary equivalent to structures over the reals. So this is actually the approach that I will, sorry. Yeah, this is the approach that I will take in this class, in this course. So now, all right, so this is the project. This is what I'm aiming for. And before we actually start doing things, let's talk in a little bit more generally about just algebraically closed fields. And let's say it like this, they're maximal real closed subfields. Closed subfields. Supposed to do straight line. Okay. So let me start first from the point of view of the real closed field. Let R be a real closed field. I'll remind you what it is. So we call, of course, several very different definitions of real closed field. Let's take this one. If and only if R is not algebraically closed, but when you add to it square root of -1, it becomes algebraically closed. Is algebraically closed. Or maybe I'll put another one, equivalent definition. R is orderable as a field, so it means you can put on it a field which orders it, but no algebraic extension of R is orderable. And no algebraic, what's called formally real sometimes, extension is orderable. And let's just recall, I'll put in two facts that we might need later. One is that every real closed field has unique ordering, which we know. Actually, it's not equivalent to being real closed field. It's weaker than that. Has a unique ordering, just given by the positive elements. X greater than 0 if and only if X is a square. I should say maybe something about the whole approach. I know that there are different levels of attendance of students in this, whatever students call, people sitting here, and I want to say that I'm aiming my the teaching, if one can say, really to people who are not experts, to, I don't know, postdoc, graduate level. I understand that there are graduate level students here. I'm trying as much as possible to aim my the course to that level. So I apologize for everyone, for people who know things, people who've seen all of this. So I will try not to go too fast, and if I go too fast, please let me know. And the second fact is that every ordered field, so this is a field after you fix the ordering, can be extends as an ordered field to a real closed field. Actually, as an ordered field, it has well, it has a unique minimal one. All right, never mind. Okay, so we have, sorry, yeah, we have so nice. Yeah, okay. So we have a real closed field, and now let K be its algebraic closure, which means you just add square root of -1. And of course, the example is R inside C. And K is a vector space of order 2, of dimension 2, vector space of dimension 2 over R. And it has, thus it has many ways of identifying it with R square, and we will identify it with R square. We identify K, and K will be used here almost always for the algebraic closure of R. K with R2 in the usual way via, well, the identification goes the other way from R2 to K. So we first fix a square root of -1, one of the two, call it I, fix one square root of -1, and now AB in R square goes to A plus BI. And this gives us identification of R2. Okay. And what we get, we know from complex analysis that talking about connection to model theory, field operations, which are maps from K to K, or from K squared to K, or from R to the 4th into R2 under this identification on K, are definable, in fact, polynomials in R. Definable in R, let me see what I mean by that. So if you take AB plus, if I think of plus as the plus on K, is just the usual addition, coordinate-wise, and B plus B, and AB times CD, so it's A plus BI times C plus DI. If I got it correctly, it's AB minus CD, and here BC plus AD. If I hope I got it right. We just get it by doing A plus BI times C plus DI. And these are polynomials, right? These are all polynomials in R over the real closed field. So what we got model theoretically, so now K plus and times is a definable field, in R plus and times. And I should say from now on, I will not, I will not use this strange plus. I will use the usual plus and times. And from the context, we will know if which operation I talk about. What does it mean that it's a definable field, like a definable group, like a definable ring? The universe is definable. The universe is R2. And the operations are definable in R because the real and imaginary coordinates functions are polynomials in the real and imaginary of the input. Okay, all right. So what do we get from that? So now every back to black, every subset, first of all, every subset of Kn can be viewed under this identification as a subset of R, sorry, to the 2n, because we identified K with R. And the K constructible sets, I will remind you what these are. So the K constructible sets, which are, to remember, the sets definable in K. So I'm using here the quantifier elimination in algebraically closed fields. So these are Boolean combinations of algebraic sets, of algebraic varieties, K algebraic varieties. They become definable, they also are definable in the real field. And I will sometimes forget to write the ordering. The ordering is always definable in the field itself. So even if I don't write it, it's there. I'm only mostly interested in questions about definability. So I don't care so much if you use quantifiers or not. But in fact, these are algebraic, the algebraic varieties in K, algebraic varieties in R. You don't need semi-algebraic. You don't need the ordering for that. So the general setting that we will have eventually is we will have R some O minimal expansion, but it will take time till we get there. O minimal. We will have K, the algebraic closure of square root of -1, fixed. So there's always some choice of square root of -1. I fixed with a fixed square root of -1, so we get identification to R2, and we want to develop, or we will develop theory of K holomorphic, whatever it means, functions of K analytic sets definable in the O minimum structure R. Okay, so we have subsets living in R to the 2n, R to the 2, functions from R2 to R2. We will have a notion of what it means to be differentiable. It's just like complex differentiable, what it means to be analytic, and we will examine. Actually, maybe, I don't know if today or on Friday, I will start even without any assumption of definability and just say a few words how far one can push this without definability. All right, but before I go there, let's look for a second at the opposite direction, the opposite. So this was from R to K. Now let's say how we go from K to R. From K to R, whatever it means. Let's start now. Let K be an algebraically closed field of characteristic 0. Okay, there's no R around, just algebraically closed field of characteristic 0. Let R sub K be a maximal real closed subfield. Okay. Maximal just with respect to inclusion. Okay, so again, we know that the algebraic closure, i.e., algebraic closure of R is R to the -1, but R is not algebraically closed by itself. Okay, so first small exercise that it's not hard, but it's not immediate. At least I couldn't see why. Maybe someone see exercise. Show that just this maximality implies, assume R is maximal. Show that under this assumption, necessarily, K is the square root of minus, is the algebraic closure of R, right? So if you take a maximal real closed subfield, then necessarily when you take the algebraic closure, you reach K. Okay, so the choice, and now we are back to this situation, right? And now once we fixed such an R, now we are back to the setting we had before. We are back to the identification of K with R squared, which R squared, it doesn't work. Okay. This R that we chose. So here's just one thing to remember when we work over the complex and the reals, we forget that sometimes. Here's another exercise. Show that inside of C, the complex number, there are 2 to the 2 to the aleph naught non-isomorphic maximal real closed subfields. And if 2 to the aleph naught requires some knowledge of model theory, then you can make yourself, I'll be satisfied even or just show at least there are infinitely many. Please show there are non-isomorphic ones. So many such. So just to point out, there is nothing canonical about the reals from the point of view of the complex field, all right? It is canonical in the sense that it has a complete order, etc., etc. But from the point of view of C, of just the complex field, there is nothing special about the real field. It's one of many, many non-isomorphic maximal real closed subfields, and on each of them we could play the game of putting an O-minimal structure on the real closed field and look what can one say about the subsets of C, the same C to the n, which are definable in this O-minimal structure on the real field that we found, on the real closed field that we found. Okay, so one, the other. And if any one of you want to think really about these problems, you're welcome, and you run into questions while working on it, or you want to run by me the argument, you're welcome to write me or to ask me when I'm at Fields. I'll be glad to discuss any of these problems that I put here. All right, okay, so what I want to do today is actually, in order to maybe convince you that the problem is interesting, that the project is interesting, I want to go back and in some sense go to the end of the project. And for the motivation that Sergey and our personal motivation to start working on this problem was a question from model theory, coming from model theory, actually the question of Zilber's trichotomy for strongly minimal structures definable in O-minimal structures. And I will not discuss the whole project, but I want to talk about one theorem that we proved back then. And so if you can say the motivation for the project was, okay, I will put it like this: Zilber's trichotomy very much related to the recent work of Ben Castle on various such questions. But in particular, we proved there the following theorem. that I want to discuss, and maybe there we will see particular we proved the following. Let R be an all-minimal expansion of real closed field R. Let K be the algebraic closure. So again, identified with R2. And let me use this curly K for the field structure of K together with possibly more sets, all definable in R. So these are subsets of K to the N. So there are subsets of R to the 2N. And all of these be a structure all of whose atomic relations are definable in R, in the all-minimal structure. Of course, you can put everything there, or everything definable in R, and then you basically will get a structure which is bi-interpretable with the all-minimal structure. If you put the real field, you put all subsets of R to the 2N, you don't get anything. You just get another way of looking at the original all-minimal structure. But now we just choose some of these. Then the theorem says, then, either you can define R, the subfield R, inside K, okay, either you can recover the subfield R inside here, or you didn't get anything new. Or I'll write it like this and explain it's just the real field. But I don't mean that it is, because you might get atomic relations. I mean same definable sets. Again, you add structure coming from the all-minimal structure to the complex field. You can say whatever the K field. And now you just allow yourself operations in the algebraically closed fields together with the new sets you got. Then either you didn't get anything new, or you can always recover back the real closed subfield sitting inside K. Like inside R2, you get back R. Inside C, you can get back R. Any question on the statement itself? Okay, let me put here the statement. And what I want to do is to try to run by you the steps of the proof if we ask this question about the complex field and the real closed subfield. The reals and the complex. Okay, so let me talk about, because here several points will come in, steps of proof when R is R, K is C. We'll see in a second where it comes in. First of all, we use a result of Ushowski that actually, if you've been to the online birthday of Udi, Dave Marker talked about this as one of his favorite results of Udi, which is extremely general, and it goes like this: if K is any expansion of an algebraically closed field And you just know that every k-definable function could be partial function. F from the field to itself, not from k to the n to k, just from k to k is k rational, so it is definable in k. Then this by itself tells you that k is just the field. You didn't get anything new. It's enough to know that one variable functions are definable in the field to conclude that every definable set is definable in the field. This is beautiful proof. Very simple, basically. Very simple. Just uses what's called Chow coordinates, elimination of finite sets. I highly recommend to look at the paper. It's in one of the first papers of Udi on expansions. I think it is the fusion paper, if I'm not mistaken. Very beautiful proof. I suggest for everyone to go look at it. All right, so now let's assume, remember, we want to show that either R is definable in K. Let's see if here it works. Yeah, here it works. We want to show that either R is definable in K or nothing added. So if we can show just that every definable function from K to K is rational, so it's constructible, K constructible, then we will be done. So what I mean, let's assume that R is not definable. So I should have put it maybe earlier. Assume R is not definable in our case. So our K, I mean the K that we had before coming from the O minimal structure. All right. So now we just want to show that every function of one variable from K to K is constructible or is rational. It's the same thing. Step 2. If we knew that K, now I'm talking about, let me just clarify. I'm talking about this K now. Sorry. I'm talking about this K. The K that expands the algebraically closed field and has O minimal sets in it. If we knew that K is strongly minimal, and strongly minimal says, if you don't know, that every definable subset of K is finite and cofinite, and the same is true in every elementary equivalent structure. If you don't know what's strongly minimal, don't worry about it right now. It will just be a black box. So if K is strongly minimal and F from K to K is, actually I could have written C, since I'm just now doing things over C. Let me write it. Everything is C. From C to C is K definable in the strongly minimal structure, then F is actually holomorphic in the usual sense, C holomorphic in all but finitely many points. So somehow, strong minimality together with O minimality tells you that functions of one variables are almost everywhere holomorphic. I will not say anything about this part. This will not be part. This is more related to work of the type that Ben Castle is doing, of how much you can exploit O minimality and strong minimality. But I will say nothing about this here. This part. This is really a delicate model theory of strong minimality played against O minimality. All right, and now step 3. in order to apply Warshawski's result, we want to show that if we have a function every R definable f from C to C, which is holomorphic at all but finitely many points, at all but finitely many points, is a rational function. Notice if we have, it's a K rational function, right? So C rational, so I'm talking about the C rational function. Notice if we have that, then we will be done. Then the theorem will be proved, because this will bring us, so by one, K is just K plus n time. So by 1 plus 2, I guess. Every definable function is holomorphic almost everywhere. So it's rational. So by Warshawski, every set is constructible, or every definable set is constructible, so the structures are the same. So this is over the complex number. So now what I want to do is to try to say something about how one will go about proving 3 over the complex field. Okay, so this goes back to option 1. What can we say about definable functions which are holomorphic, definable in O-minimal structures, and holomorphic just in the classical setting of the complex field? Okay, so let's talk about proof of 3 over C. Because why is it much easier? Because we have the whole classical theory of complex analysis working for us. So what do we have? So we assume that F is from C to Z1, minus Z1 to Zn into C is holomorphic. And definable in an O-minimal structure. In an O-minimal structure. Okay, we want to show that it's rational. How shall we do it? Let's see that actually, and this, in some sense, if you want the whole complex analysis in O-minimal structure, from my point of view, comes down to this particular point that I'm just going to talk about now. Let us see. So claim F has a pole at each Zi. So these are isolated singularities. Let us see that that you can only have poles in the O-minimal setting. Well, right, this is interesting. Okay. In the O-minimal setting, every singularity is either a pole or removable. A pole, sorry, or removable. As a pole, at worst a pole, I guess, or removable. I mean that it's not an essential singularity. Proof. All right, so let's call it Z0. So say that Z0 and isolated singularity of the holomorphic F. Let us see that it is not an essential singularity. So, right, these are the options. Either it's an essential singularity, or it's a pole, or it's a removable singularity. If Z0 is an essential singularity, then we know by complex analysis, then, right, and this here we're using, I guess, even just first class, I think, this part, not even beyond the first class of complex analysis. We know that for every R, if you take a neighborhood, the punctured neighborhood around, let's call the punctured neighborhood, let's put a star like this, right? We know that around every isolated, every essential singularity, the image of the punctured neighborhood is dense in C. Every punctured neighborhood of an essential singularity is sent to a dense subset of C. So now we just have to be convinced that this cannot happen when the function is definable in an omnimal structure. Let's see why this is the case. So one way to see that this is dense, it means that, i.e., if you look at the closure, if you look at the graph of F restricted to B Z0R, and you look at its closure, then you get the fiber above Z0 fully contained in the closure of the graph of the function. Okay, take a second to think why this is the case, but it's easy to see that this is true. Actually, I didn't need even for all R. It just worked if I did it with the punctured C, but never mind. But now let's look at dimension. What is the dimension of a function, of the graph of a function defined over an open set? Well, it's the same, it's in bijection with the open set. So let's call this gamma. The dimension of gamma as a set definable in an omnimal structure, the dimension of gamma is the same as the dimension of the domain. They are indefinable bijection. And this is dimension 2. Okay. Gamma is clearly disjoint from the graph of F because F is not defined. So, sorry, not gamma, the fiber, right? And the fiber above C is disjoint from gamma. So if it's in the closure, but it's disjoint from the set, it means that the whole fiber is contained in the frontier of gamma. Remember, I think I saw that, which means the closure of gamma minus gamma. I saw that Garrett spoke about this. But we know by omnimality that the dimension of the frontier has to be smaller than the dimension of the set. By omnimality, for every definable sets, the dimension of the frontier, the closure of, is smaller than the dimension of X for any definable X. X, but this dimension, because you have the whole of C, this is clearly dimension 2. And the set gamma has dimension 2. So we get a contradiction. Right? And if there's anything that you want to remember from complex analysis in the omnimal setting, is this point, that you cannot have an essential singularity realized by a definable holomorphic function in an omnimal structure. Okay, this is really the punchline of everything in some sense. And now, to finish is not hard. I will not. So now we know. So I'm going back, right? So each Zi is either removable. So I'm going back to the setting when you have a function with finitely many poles, or pole. But now it's not hard to see. I mean, you take out the essential, what's called the principal part, sorry, of every pole. So now you do something, I think I wrote it correctly. You go over all the poles, and from each pole, you remove the what's called the principal part of the pole, the part which makes it, I will say something, I think I have the coordinates right. The indices ZI with the J, and you remove, do you need even, I don't think you need even to remove polynomial. So these, each one of them, this is the principal part of what's called the principal part. It's a part in the expansion with negative powers, the principal part of the pole. And now you're left with a bounded function because you removed all the problems, and this is bounded now. Is it? No, sorry, not yet. So, but this is now in this writing now has no poles, has only removable singularity, has only removable singularities. This part, of course, is a rational function, the part that we added, right? And now you play a small game, and if you've done a course in complex analysis, you probably can guess, you show that also at infinity, you just by applying 1 over z, also at infinity, f as a pole. Said differently, you can subtract from, so now f of z minus, let's call this box, I don't want to copy this, minus some polynomial, So once you took care of what happens at infinity, you are left with a bounded set. By Roche, you apply, by Liouville theorem, it is constant. So f is rational. We remove the rational function, we remove the polynomial, we got a constant, so f is rational. All right, okay, so let's go back for a second and see what it is that we used from complex analysis. First of all, we use the fact that we have a notion, of course, of a holomorphic function, which we don't know what it means in general when we don't work over C. We use the fact that points are either removable or singular, or whatever essential means. At least it means that we will need something like that, that this is dense in C. And this part, right, we will have for free from O minimality. But we use something like Liouville theorem. If we want to move to other settings, we need to prove results like that, that if the definable function is holomorphic and bounded, then it is constant, whatever holomorphic means with respect to this new algebraically closed field. All right. So this ends the theorem that I mentioned from model theory that Sergey and I were after. But let me, I want to bring back the theorem. Any questions about that? I think it's something that you can mostly recover if you go through the notes. Let me go back to the result itself. Here, this is the theorem. So again, the theorem said that if you take an expansion of the algebraic closure of R, so of course we needed, in order to pull off the proof that I mentioned, we needed to develop all this complex analysis in the setting of, in this arbitrary setting of a real closed field and its nominal expansion. Once we did all of that, we could basically have exactly this proof that I wrote down is the proof that we wrote for this general result. But look, I think there are some interesting corollaries of this result. And this was pointed out to us by Marcus Tressel. Let's go back. It goes back to the issue of if you start with an algebraically closed field of characteristic 0, what can you say about this maximal real closed subfield? So assume K is algebraically closed. The characteristic of K is 0. And now assume that we have two different, that's all. You don't need non-isomorphic, you don't need anything, you just need two different, just not identically the same as a set, two different maximal real closed subfields. So it means that you can identify K once with R12, and also you can identify it differently with R2. They can be isomorphic, they don't need to be isomorphic, it doesn't matter. Now, choose arbitrary X in K to the N. Notice that if X is in K to the N, it's a subset of R1 to the 2N. It also can be viewed as a subset of R1, R2 to the 2N. And now, assume the following. How should I write it here? Yeah, let's call this R1. Let's call R1 the following. The real closed field R1 with its plus and times, the same one coming from K. Let's call its ordering less than 1 and put X as a subset of R1 to the 2N. Okay, we now view X as sitting in R1 to the 2N. Do the same thing with R2. Sitting in R2 to the 2N. Okay. Let me point out that if X was constructible, or if X was a K algebraic variety, yeah, if X, sorry, is an algebraic variety in the sense of K, it will become an R1 algebraic variety and an R2 algebraic variety, right? We agreed that, well, actually R1 definable, but actually it's an algebraic variety. You just look at the imaginary and the real parts of the sets. And so if X was an algebraic variety in K, there will be no problem because both R1 and R2, X will be definable in R1 and definable in R2. Everything is fine. But in general, we don't know what kind of a strange object you will get, but assume both are O-minimal. Right? X is just an arbitrary set. Assume now X in an arbitrary set in K to the N, such that when we expand R1 with it, we get an O-minimal structure. When we expand R2 with it, we get an O-minimal structure. For example, like X being a K definable set, or K being X being a K algebraic set, this will be the case because they will be actually already definable in R1 and in R2. Then X is K constructible, K definable. So the only way that a subset of K to the N can be O-minimal with respect to two different real closed maximal subfields is if X is already constructible in the sense of K. Okay, again, if we started from a constructible set, then it's automatically true because X will be definable in the field R1. The field R1 is O minimal, so we will not be doing any expansion. Same thing, it will be definable in R2 in coordinates, so there will be nothing. But the statement is the converse. If it is definable in two structures which are O minimal, the only way it can happen is if X was already definable in the algebraically closed field K. Let's look at the proof of that. This is the theorem that we have. Proof. By theorem, the only theorem actually I quoted today, if X is not K constructible, K definable, constructible to remember. Sorry, I want to put this theorem here. Or let's say K definable, so it will be, I will use the same terminology I will use in this theorem. Then, if we apply the theorem to the structure R1, right? If we apply our we apply our theorem to this structure, then R1 is definable in K plus times X. Remember, we said, what did the theorem say? That if you expand the algebraically closed field by an O minimal set, then either R1 is definable, and if, sorry, either X is already definable in the algebraically closed field K, or you can recover R1 in just the algebraically closed field K with the additional structure that we put. Similarly, R2 is definable in K plus times X. So R1 intersection R2 is definable in K plus times X. Okay, but K itself is definable, say, in R1. So in particular, R1 intersection R2 is definable in the O minimal structure R1, which was R1 plus time less than 1. Right? Because K is definable in R1 and X is definable, of course, in R1. Yes. Same. K is definable in R1, but then we get a subfield of R1, which is definable in an O minimal structure, and it's not hard to see, but so here is a exercise number 3 for today. If R is an O minimal expansion of a real closed field R, it's curly R, then R has no proper definable subfield. Then R has no proper definable subfields. In particular, R1 intersection R2 has to be equal to R1. Okay, so hence R1 intersection R2 equals to R1, which implies that R1 is contained in R2, and similarly, R2 is contained in R1. So we get that the two fields are equal. Contradiction. Okay, so I'm looking at the corollary that we just proved. If we have an algebraically closed field, and two different, and a subset of k to the n, no, this is not working. And we have an algebraically closed field k. We have two maximal real closed subfields. And we have a subset of k to the n, which is O minimal with respect to the two fields. Then it actually, the only way it can happen is if X was actually just definable in K field. It's just a constructible, it's a complex analytic, if you want, object. It's a K analytic object, a K algebraic object, sorry, it's a complex algebraic object. And this is the only way that the set can be O minimal with respect to both. Now, let's point out that this is actually useful. Although at this point, I can only prove things which are known to be true, but I have a feeling that maybe one can do better than that. So here is another corollary of the first corollary. Let R, it's a family of results, if you want, B. No, sorry, I'll write it like this, B O minimal, expansion of R, X in R, in, let's do it over the real even. It's okay, let's do it all over the real. Although it works in any, it doesn't matter, of R plus times X in C to the n and R definable set. Assume that there is some automorphism, field automorphism of C. I'll write it like this, C plus. There is some of the real closed field, which is different than conjugation. In particular, it doesn't keep R fixed, such that which leaves X invariant, sigma of X equal to X, then X is complex constructible.
Yes, sorry, Kobi.
Yes.
You wrote sigma equals Z bar.
That's different. So thank you. Yes. Okay, now let's not get confused. Of course, it's not true that any set which is invariant under even all automorphism, even if you have a set even invariant under all automorphism, it's not constructible, right? The family of algebraic number, the set of algebraic numbers is invariant under all automorphisms as a set, but it's not a constructible set. So just being invariant, even under all automorphism, doesn't make you constructible. You need to know more than that. And here it's enough even just you have just one one automorphism which is different than complex conjugation, and the set will become constructible. Let's see why, how it follows from the result of Peterzil. So, okay, proof. Since sigma is different than complex conjugation, then sigma of R is not R. Because if sigma of R is R, you immediately force, right? You will fix it pointwise because of density, whatever, and then it will be automorphism. Of course, not idea, I should say. Sorry, it's not clear. Yeah, right. We don't want complex, we don't want trivial automorphism. And then let's see what it does to X. So sigma is an automorphism, so in particular, and everything is definable, so it will send this to sigma of R. Yeah, let's put the reals here. Sigma of the reals. Plus is sent to plus, time is sent to times, and X is sent to sigma of X. But this is X. So we will get that X is O minimal, and this is of course O minimal because, yeah, I should say that. And this is O minimal with respect to the ordering, which is unique. I didn't write it here. So this is O minimal as well, right? Because if they are isomorphic and one is O minimal, the other is O minimal. But now look, we have X O minimal with respect to two different fields. If X is O minimal with respect to two different fields, by Peterzil theorem, we get that X is constructible, complex constructible. So by Peterzil, X is complex definable. And so I'm using constructible and definable interchangeably when I talk about C. All right, so it's a good question. How can you identify definable sets in O-minimal structures and find a single automorphism which leaves them invariant, but instead it's already applicable in cases when we know where sets are invariant under all automorphism. Even this is not a trivial matter. So, for example, what you get from that is that assume you have a family of sets xt, t and t, which is C definable. C definable. And let's say xt in C to the n or in projective space, it doesn't matter for every t. And now it's very common in model theory to try to ask about various properties of the parameters and to ask, okay, is this again constructible? What can one say about this? So, for example, we get from this something which is an exercise in algebraic geometry, but I'm told it's not a trivial exercise. The set of all t and t is such that, for example, the Zariski closure of xt is irreducible is itself constructible. And similarly, instead of the Zariski closure is irreducible, the Zariski closure has 7 irreducible components, is constructible. Why? Well, how can we see that? Okay, so well, being irreducible is clearly invariant under all automorphisms. So let's call this set, sorry, I'll put here T1. So because being irreducible is clearly invariant under automorphism, so T1 is invariant under all C automorphisms. Let's say everything is over the empty set, right? Let's say definable over the empty set. C automorphisms, because the notion of irreducibility is invariant. But T1 is definable in the O minimal structure. Why? Because being irreducible, it turns out, is exactly the same as the smooth points. Maybe we'll get to that when we develop the theory, because T1 can also be written as the set of all T and T, such that the regular points of xt, this manifold is connected topologically in the usual sense, in the Euclidean sense. Right? It turns out that the Zariski closure of the smooth points are the Euclidean closure of the smooth points are exactly the Zariski closure, and one for if the regular points are connected, then the Zariski closure is irreducible, and we know that this is definable in O minimal structure. By the way, it's a non-trivial point that this is definable, right? This is definable in parameters. I'm not sure if Garrett's talked about this. It follows. If you think of that, if you're not familiar with that, there is clearly not one formula that does it, but it's a result of cell decomposition that it is true. Same if you wanted to say that there are k components, k connected components. This is the number of connected components, the same as the reducible component, and it's definable in O minimal structure. In R. So by the corollary we said, we needed only one automorphism, it's invariant under all automorphism, then so constructible. Right, and you can probably look at various properties like this and ask yourself, okay, this invariant, it's most properties that I can think of are arise in settings in which they're invariant under all automorphisms, but you can ask yourself in more delicate situation, maybe can I find a single automorphism which is not complex conjugation, which will keep this set invariant, and then you can prove algebraicity, right? In the project of all this definable chow, etc., I wonder if one can use such techniques as well to prove algebraicity or constructibility. And I'll just put one example, which is more technical. If you know what it is, okay. If not, don't worry about it. Or if you have, I'm sorry, I'm using this fancy word. S is a Shimura variety. Then, and you have, and all XTs, let's say, are subsets of S in the family, then the set of all T and T such that XT is what's called, I'm just aiming it for people who know what it is so-called weakly special, for example. Not special, because special requires it to contain rational points, and we cannot identify definably which one are rational points. So I'm just putting it in, don't worry if you don't know what it is. It's not where we're going. Is also constructible. See, constructible. Why? Because the setup of Shimura varieties allows you to pull the problem back up and ask questions where there's certain sets, the pre-images are linear subspace, C-linear subspace, etc., etc. So I'm just putting it in, and again, don't worry if it's if all these words don't mean much to you. Don't worry about it. Just to this is a less trivial setting where you need some analytic setting in order to see that the set T1 is definable, but using the fact, which I hope is, I'm almost sure it's true, that the property of being weakly special is invariant under automorphisms, under complex automorphism. I assume this was true. You get constructibility of the parameter space, of the parameter set. Okay, so basically, this is what let's see if there's anything. Okay, so let me now summarize what we did. So this was like an introductory class to give motivation. So we saw how complex analysis in the O minimal setting can be useful to prove, let's call them in general, algebraicity results. By algebraicity, I really mean constructibility. Since about subsets of C to the n, and more generally, K to the n. Okay, algebraically closed characteristic 0. See, yeah, I should say that from the point of view of model theory itself, being algebraic and being constructible is hard to distinguish, because we talk about definability, maybe definability which is quantifier free. And so quite a lot of work sometimes in applications goes into this delta, even I think in what Jacob Zimmerman will do, into this delta between algebraic and between constructible and being actually algebraic. So often there is work, and this work, I think, is not model theory. So mostly the results that we will be talking about eventually will be constructibility results, means definability in the algebraically closed field and not algebraicity. Okay, so this is one comment. And so the goal of the course, so I now repeat what I plan to do of the course is one, to define and develop basics of what it means to be K-analytic, basics of K-analytic theory, and prove results like, let's say, the Liouville theorem for definable functions in O-minimal structure, let's say in one variable. Two, identify. So this is one, for example, seems useless if you're interested only in things over the reals, over the complex numbers, because we know all these theory over the complex numbers. Okay, so everything that I will do at the beginning, the setup, in some sense, you can say, oh, I know it over the complex numbers. I'm only interested over the complex numbers. All the basic theory is unnecessary. Okay, I'll try to convince you with theorems like the one that I talked about today that it could be useful to do it in more general settings. Second, identify properties of definable k-analytic functions and sets of definable k-analytic functions and sets. In the setting, when I say definable, I will always mean minimal, even if I forget to say that. E.g., what we did today, this was one special property, no essential singularity. No essential singularity. Three, as a result of that, I hope to say something about so-called the definable Chow theorem. Chow theorem that says that I'm not sure how far every okay, I will not write it, but I'll say it in words. Every definable k-analytic subset of k to the n is algebraic. Right, so this is special properties of definable Chow theorem. Special properties, sorry, of analytics. So this is part of 2. So no essential singularity is 1. Definable Chow theorem can be a manifestation of the fact, actually, that there are no essential singularities. It's part of the same feature of orthogonal structures, that there are no essential singularities. But because we want to develop it in the general setting of an arbitrary real closed field, there are problems that immediately arise. And the difficulties in part 1, we cannot use the basic tools of of complex analysis. What do I mean by that? We cannot use convergent power series or power series, which is, I think, attributed to Weierstrass' point of view to complex analysis. Why can't we use power series? Because okay, let me say, I put it somewhere, but here is another exercise. If you haven't seen it before, show that there are actually for every minimal structure, you don't even order for every ordered structure, but linearly ordered, there is, so this is for the model theories, there is, if this is M1, there is N1 elementary equivalent to M1, such that no sequence A1, A2, A3 converges. No, of course, except the constant sequence. No sequence AN in N1, there is no need even for definability, converges at all. All right, so definitely there are no power series. When we work in this general setting, we cannot use power series because no sequence might converge except the constant, right? No non-constant. It's a nice small exercise to just convince yourselves that this is doomed. We cannot use power series. And the other tool, of course, of complex analysis is integration. And we cannot use integration. Well, at least the classical integration also will require, if you do it via Riemann sums or Riemann integration or similar integration, you cannot hope for these sums to converge for the same reason, to have a limit in this general model theoretic setting. So the two most important tools that you've seen in complex analysis are out of reach for us. Okay, and the alternative approach is something that we were lucky to discover in a small book by Wyborn, is topological approach to analysis, to complex analysis, which to a large extent is based on a beautiful book, on a book called Topological Analysis from the 60s, and actually based on papers of the group of people that around Wyborn, probably students by Wyborn. And I'm sorry for this, but I have the reference, of course, on the reference list. And it's some sort of magic that together with definability in homeomal structures, actually one can say maybe the most important replacement of integration is the notion of a winding number. And we'll see that winding number is fine. We can define winding numbers in the O-minimal setting, and the starting point will be this. And based on that, we can develop all of this basic complex analysis just based on this notion of a winding number. Maybe I don't have to use all we can make it a bit short this time, because this is a natural place to finish. There's one thing, what else I wanted to say? Yeah, let me say that I will start everything actually in order to slowly go to the place where definability is used. Actually, we will start still from just the beginning, maybe the first 15, 20 minutes, we will start from general topological fields with some examples. And I didn't study this notion very deeply. I looked at one or two books, and we will see how far we can push the theory just based on the notion of a topological field. And then at some point, I would say, okay, maybe this can be done. This is I'm sure some people worked on it. I looked yesterday, I saw that there is some work, even recent work. But so after the first, maybe 1/3 of Friday's class, I will go to definability and try to really develop the basic of the theory as much as one can do in such short course in the O-minimal setting. Okay, so the plan is to start, probably to start on Friday talking a little bit about topological fields, and then slowly converge towards the O-minimal setting. And then I will develop probably for about, I don't know, 2/3 of the remaining classes, maybe 4 classes. I will talk about one variable functions, and then I will talk about several variables, and hopefully say something about analytic sets and all this problems. So I'll stop here a bit early, but I don't want to start this whole subject of topological fields now. Any questions that I can answer? Please feel free to ask. All right, so I should say that in some sense, I will not assume much knowledge of complex analysis, because I'm not working in the classical setting or in elementary equivalent. Of course, if you know the basic complex analysis, it will help you because you will be able to draw analogies, but hopefully I can develop some of the basics just hands-on from just using definability theory. So we will get for free, as we will see, actually we will get for free the local theory of complex analysis we will get using O-minimality. I will say something, I mean, the local general theory of complex analysis we will be able to get using O-minimality, and we will see why next time. Okay, so we end here. for now. You can have,
Okay, I will stop the recording.
all right. So on Friday,